Antonino, we forgot to ask you, we're going to record your talk and make it public, so if you have no
objection.
Actually,
no
it's
problem.
already recorded. You cannot change your mind anymore.
Okay. Well, it's a pleasure to have here Professor Antonino di Lorenzo. He got his master's and PhD at Universidade Catania in Italy. Then he made a tour around the world, different postdocs in Delft, Holland, Stony Brook in the United States, back to Italy at CNR. Then he came to São Carlos, and then back to CNR again, and he has been a professor here at in Uberlândia with us since 2009.
Yes.
2007.
9.
2009. So today he's going to talk about Thomas precession revisited. So it's the microphone is yours.
Thank you for the introduction, and thank you for the invitation. So, a good afternoon, everybody, or good evening, or good morning, depending where you are. Here you can find the outline of this talk. I will talk about Thomas precession because in the past few years I have studied the relativity of accelerated frames, and this is a natural topic that comes. I will give you the conclusions right away, which are not conclusions then, it is a summary. What I will show you in the next 50 minutes or so is that the tree vector that is being used defining spin in the lab frame is not correct. It does not transform as you expect a vector should transform according to relativity. So I found the correct vector using the relativity of simultaneity. I will show that when you describe how this vector carried by an accelerated particle moves in the lab frame, it makes a very complicated movement, which is not a simple precession. And I will show you how, from this complicated movement, you can extract a precession term, which has a linear part, which I call Thomas precession, and also a nonlinear part, because it depends where the spin is pointing. And my value for Thomas precession is different from the one which was accepted so far. I will show that this other value does not describe the motion of the spin, but does describe a rotation of a reference frame. And an important consequence of these results is that a recent experiment made at Fermilab, where they measured the G-2 anomaly for muons, and where they found discrepancy with the standard model, might need revision. So, well, what is the motivation of this work? For me, to be honest, when I started this work about 1 year ago, it was just curiosity. I was working with accelerated frames, and then this topic came out. And then, by a lucky coincidence, when this work was done, the results from the Fermilab experiment were divulgated. And so you can not be curious about the same things I am curious. So I think that analyzing the Fermilab experiments is a sufficient motivation for you to listen to this talk. Let me summarize what were the findings of this experiment. I will talk about this again only at the end of the talk. There is a lot of material to cover to get there first. So what they found was that the G-factor anomaly for the muon is several sigmas away from the prediction of the standard model. Here there is the result of the Fermilab experiment. There is another result obtained around 2000, basically the same experiment in Brookhaven, which is compatible. And this is the average of the two results. And you can see that there is some discrepancy here. I will show that maybe in doing the analysis of the data, they did not include a source of error, which might increase this error bar and make the results compatible with the standard model. So let me give you some background information. You know that in Newtonian mechanics, when you consider accelerating frames, there are non-inertial forces. Once you specify the movement of the origin of the reference frame, which could be, for instance, a particle, you have not specified the frame, however. You have specified, just its origin. You have to specify also the axis. And among the infinite reference frames which make a certain motion, there is a special one. The one where you do not see any Coriolis forces. And in classical mechanics, Newtonian mechanics, this special reference frame is characterized by having its axis parallel to the axis of the lab frame. The axis of the accelerated frame do not move. You see that the frames here below, in this row below, do not move relative to the inertial reference frame. However, in relativity, things are a little bit different. Here I will show in relativity, special relativity, the motion of two reference frames that are attached to the same particle. One frame is given by this solid axis, the other frame is given by the dotted axis. You see here that the dotted axes are wobbling, but they are not making a full rotation as the particle moves. Instead, the solid axes, in addition to this wobbling, are making a rotation. You are seeing that the angle between the axes is not 90 degrees, and that the axes have not a fixed length. This is because of Lorentz contraction. The axis along the velocity of the particle will contract, and this causes the angle to change. So you cannot avoid this wobbling because of the Lorentz contraction. And what might be counterintuitive is that if you use these axes here, which appear to be rotating overall, you will see no Coriolis effects. So this special reference frame, where the axes are wobbling and rotating, is a frame where you see no Coriolis forces. You just see the basic non-inertial forces. The other frame, the dotted frame, where the axes are just wobbling, instead is a rotating frame, in the sense that there you see Coriolis forces. So I will just recall briefly Lorentz transformations. There are special Lorentz transformations which are called Lorentz boosts, but in textbooks very often they do not make any distinction, which are given by this formula here. If you take the velocity along the x-axis, you will recognize the familiar formula for any basic textbooks in special relativity. This transformation is characterized by this symmetric matrix, is a Lorentz boost. Now we have to consider that the parameters in this matrix, the gamma coefficient, the Lorentz coefficient gamma, the velocity, change with time because we are considering an accelerated particle, okay? Once you define Lorentz boost, you can define a special reference frame, which I call the boosted frame. Basically, what you do is you stay in the lab, you measure the velocity of the particle in the lab, it is V0. You apply a Lorentz boost to define the reference frame of the lab at that time. You go at another time, t, in the lab frame, it is important where the time is measured, of course. The velocity of the particle has changed. You apply another transformation, and you do this continuously in time. What we are doing by making this position is you are defining a rotating accelerated frame. Rotating in the sense that in this frame you will see Coriolis forces. And this procedure here corresponds to the dotted axis here, okay? So these axes are making a minimal rotation because we are applying pure Lorentz boosts. Lorentz boosts do not rotate the axis, so to say. There is another reference frame which is more important, it is fundamental, which can be attached to the particle, and it is the Fermi-Walker frame. It works like this. At time 0, I apply a Lorentz boost, and so I am defining the axis of the particle. Now, I am in a reference frame where the particle is instantaneously at rest. Real time delta t prime in this frame, the velocity of the particle changes. You see, I am using primed quantities because I have changed the reference frame, okay? Now, what I do, I apply an infinitesimal Lorentz boost with this infinitesimal velocity. Go to this new frame, the particle velocity changes again, I apply another Lorentz boost, and so on, until I get the final velocity of the particle in the lab at time t. Of course, this will give you a differential equation in the end. When you make this procedure, you are making what is called Fermi-Walker transport. It was Fermi who invented this in 1921, I think. It was the third article Fermi ever published. And importantly, when you combine Lorentz boosts one after the other, the result is not a Lorentz boost. Lorentz boosts do not form a subgroup. The important thing is that the Fermi-Walker frame is a non-rotating frame in the sense that an observer using this frame will not see Coriolis effects. Sorry, I lost my... Yeah. Now, once we have defined Fermi-Walker transport, we can define the Thomas Wigner rotation. When you combine all those infinitesimal boosts, you get a Lorentz transformation, a general Lorentz transformation, which can be written as a product of a boost followed by a pure rotation. You can see that it is possible to demonstrate that this rotation after the boost is characterized by this omega primed rate of rotation. It is an angular velocity. This rotation describes the movement of the axis of the boosted frame relative to the Fermi-Walker frame. So this is called the Thomas Wigner rotation, and it describes how the axis of an accelerated frame rotate with respect to the axis of another frame. But this is not what I want, because I want to describe the spin in the lab frame. I do not care what happens between two accelerated frames, okay? And there is another possible decomposition of the same Lorentz transformation, which consists in making first the rotation and then the boost. In this case, you can see that you define another angular velocity, which describes the rotation of an auxiliary reference frame, which is at rest in the lab frame, but the axes of which are rotating. This is an alternative definition of Thomas Wigner rotation that you find in the literature. Indeed, there is disagreement, because people often confuse which decomposition is being considered. And also this decomposition, this rotation here, does not describe how the spin moves in the lab frame. And that's what I want. I want to find the precession of the spin in the lab frame. What happens is that the spin makes a very complicated motion. You can see that it stays normal to the trajectory most of the time, then it decreases. This is because of Lorentz contraction. When the spin is parallel to the velocity, when the velocity is very high, Lorentz contraction will make it, the component, very small. However, from this picture, it is not clear, so I will show you in the next picture, not the spin, but the direction of the spin. So this green vector is the unit vector in the direction of the spin. So there is no Lorentz contraction here to confuse things. You see that the spin stays normal to the trajectory most of the time, but it rotates a little bit around this normal. You see, now it is rotating, and now you see all of a sudden it ripped on the other side. When the spin is almost parallel to the velocity, it will precess more rapidly. So what you are seeing here is that there is a nonlinear contribution to the precession. The precession depends on the direction of the spin. And I will quantify this in a little bit. First of all, we should define what is the spin in the lab frame, because I've shown you a 3-vector in the lab frame. So let us look at Minkowski space. Minkowski space, sorry. So we have an inertial reference frame, which is represented by a straight line in Minkowski space. And you have the axis, x and y. There is z, but I cannot represent in 3 dimensions, of course, because 1 dimension is time. And then there is a particle which is accelerating. For instance, it is making a uniform circular motion. In Minkowski space, an accelerated particle makes a curved world line. This particle is carrying some property, the spin. The spin is a vector in Minkowski space. It is a 4-vector, and it is perpendicular to the world line. So at every point of this line is attached a vector. I am showing only 2 of these vectors. There are infinitely many, of course. And I said that the spin is perpendicular to the world line, but as you can see, it does not look perpendicular because it is perpendicular in the Minkowski metric, where there is a minus sign in the time component, okay? So, I am representing it in our space, which is Euclidean. But now, if you take the tip of this vector here, of this spin, as time goes by for the accelerated particle, this tip will trace another curve, another world line in Minkowski space. Now what you do? As an observer in the inertial frame, you consider an hyperplane of simultaneity, which is a plane perpendicular to the world line, to your world line. This plane will meet these two curves in 2 points, which are simultaneous for you. This is the relativity of simultaneity. Then you construct the vector which goes between these 2 points. This vector t, this red vector t, is the spin in the lab frame, defined according to relativity. However, this is not what is being used in the literature. In the literature, they do something different. They take the spin at some specific time for the particle, and they decompose this spin in 2 components. A component parallel to the world line of the inertial observer, and the component perpendicular. So they write this spin as S0 time component S, space component. And they take this space component S as the spin of the particle in the lab frame. However, if you look at how this vector S transforms, it dilates by factor gamma in the direction of the velocity. Instead, the vector t contracts by factor gamma, which is how a vector should behave. And the 2 vectors are related by a simple relation. Here the velocity is in units of c. And in principle, you can decide which is the correct definition in the lab by experiment, because to the spin is associated a magnetic field, a magnetic dipole. And this dipole will create a magnetic field. So if you accelerate a particle in a direction, if the correct spin is S, it means that in that direction you should detect a very strong magnetic field. Instead, if the correct definition is T, you should detect a very low field in the direction of the velocity of the particle. I will show that it does not matter which definition you use when you study Thomas precession. This is a result, because a priori it was not clear, because these are 2 different vectors. So, first thing, let us write the equation for the spin in Minkowski space. So think that Minkowski space-time is absolute. It does not depend on the fact that there are observers which represent their vectors with the quadruples of numbers. Then, if you assume that the spin obeys a first-order differential equation, linear, in S, you have this equation for the 4 vector. The derivative of the 4 vector equals a tensor applied to it. You see this tensor here is formed on the right, the second term, is formed multiplying the 4 velocity of the particle, which is the tangent to the world line, so it is a geometrical quantity, and the acceleration of the particle, which is the normal to the world line, another geometrical quantity. So they are defined independently of the coordinate system. This product here is an external product. There is no dot. So this here is a tensor written as a dyadic. And this combination here, UA minus AU, is the generator of Fermi-Walker transport. In addition to this term, there is a term which depends on an applied external field. You see that there is a coupling constant here. And here, you see there is no coupling constant. Because this is a purely kinematical term. The coupling constant for spin is the charge, so it could be the charge of the electron, divided twice the mass times the energy factor, a factor which for electrons and muon is very close to 2. Next, we must require that this applied field phi is skew-symmetric. Why? Because spin must be conserved. The norm of the spin must be conserved. It should be always h bar over 2, for instance. And this can be achieved only if this tensor here is skew-symmetric. The Fermi-Walker transport is naturally skew-symmetric. So you have to worry only about phi. In addition to this, you have to require also that this tensor field here can be written as a sandwich between with the electromagnetic field in the middle, and here to the left and to the right you have the projection operator in the direction perpendicular to the word line of the particle. This form guarantees that the component of the spin parallel to the word line is constant. In particular, we want that the spin is a pure spatial vector for the particle, that this component is always 0. Finally, you must consider also that the acceleration depends on the field. You are seeing here Newton's second law in relativity. Mass times the force acceleration equals Lorentz force. When you use this equation and replace here, you find a very famous equation, which is the Bargmann-Michel-Telegdi equation. Actually, there is a missing term here, because if you have a spin in an electromagnetic field, you should consider that there is also a Stern-Gerlach term if the magnetic field is not uniform. So this equation, this Bargmann-Michel-Telegdi equation, is not complete. This is still an open topic. But now let us see how this equation translates in a given reference frame. So we will work from now on with 3 vectors. Let us start with the simplest equation. If I go in the reference frame defined by Fermi-Walker transport, so I move with the particle and I transport my axis with the Fermi-Walker transport, the equation of motion is given by this simple formula. It is a pure rotation. And if you see this from the point of view of the particle, it all makes sense. The principle of causality is obeyed. Because imagine that you are an electron orbiting a proton. Now, from your point of view, what do you see? You see a proton. The proton has a positive charge, so it generates an electric field. So there is a force that the proton makes on you. But at the same time, you are at the origin of the coordinates. So you are at rest. So this force must be compensated by some other force. And here is the principle of equivalence, which says that since you are accelerating, you will see an effective local gravitational field. And this gravitational field is compensating exactly the force made on you. In addition to this, you say, well, but the proton is moving, and the moving charge will create a magnetic field. And this magnetic field is making my spin precess according to this equation here on top. So you see, it all makes sense. You can explain the words if you use a Fermi-Walker frame. However, if you go to another frame, which is rotating relative to Fermi-Walker frame, the equation for the spin is a little bit more complicated in the sense that you cannot explain it in terms only of the magnetic field, but you will see an additional Coriolis rotation, which has no explanation. You cannot explain with the nearby bodies. You cannot explain with the local gravitational field. So the principle of causality does not longer work here. That's why Fermi-Walker frames are so important. And finally, let us go where we really want to work. We want to study the spin in the lab frame. Now you can see that starting from the general equation, you get this apparently complicated equation, which is a matrix equation. The derivative of a vector equals a matrix applied to the vector. And this matrix depends on time, because all the elements here depends on time. You are seeing here, I am multiplying a velocity with an acceleration, for instance. This is an external product, a dyadic product. This represents a matrix. So it's a matrix with components bx, ax, bx, ay, and so on. Here you see the electromagnetic field multiplying a vector j, which are the generators of rotations in 3 dimensions. So what you can notice is that this equation here does not describe a rotation, because the matrix is not skew-symmetric, which leads to the mathematical problem. Given a matrix equation for a vector, how do I extract a rotation from this equation? So you have the derivative of a vector in any number of dimensions, does not matter now, equals a matrix applied to the vector. And this matrix is not skew-symmetric, because if this matrix were skew-symmetric, this would be a rotation. There would be nothing to do here. But when this matrix is not skew-symmetric, we must find a way to extract a rotation from this equation. Let us see how it is done. First step, you take the matrix and you write it as a sum of a symmetric and a skew-symmetric part. Second and third step, you separate the equation for the norm of the vector and the equation for the direction of the vector. So what is important is the second equation here below. Now you see that there is a skew-symmetric matrix applied to the vector, and then there is this symmetric matrix applied to the vector. Next, you notice that this symmetric matrix applied to the vector is the same as applying this skew-symmetric matrix to the same vector. And when you make the commutator of 2 symmetric matrices, you see here M is the symmetric part of the matrix M, so it is symmetric. Here I have the external product of the vector V with itself, which is a symmetric matrix 2. So this, the commutator of 2 symmetric matrices, is a skew-symmetric matrix. And that's it, we are done. So we can write the equation for the vector as a skew-symmetric matrix, which is split in 2 parts, a linear part and a nonlinear part, because you see this matrix here, the second matrix A, depends on the direction of the vector. And here we are. Now we need only to apply to the spin. So let us consider the simplest case. When lambda is 0. Lambda is 0 means that I have a spin which has no magnetic moment. It is an artificial situation. Why I'm doing this? Because it is simpler, and because this way the only contribution to the rotation is due to the kinematical term. It's not due to the external field. When you do this, you find that the linear term is given. Here, the linear term is given by this expression, Well, the nonlinear term is a function of the spin direction. It's given by this expression here. And you see that even when you sum the two, you do not get the Thomas Wigner rotation, which up to now was considered to be identical to the Thomas precession. But what I'm saying is that they are two distinct processes. Thomas precession is describing the rotation of the spin in the lab frame. Thomas Wigner rotation describes a rotation of a reference frame relative to another. They are related, but they are not the same thing. Now you can consider also the special case of a planar motion, in which case the component of the spin perpendicular to the plane is conserved. In this case, the nonlinear part is a little bit different. I simplified a little bit the theoretical discussion here. And now let us go where it is more, let us consider two applications. The first application is a particle, for instance, an electron in an atom. So you have a Coulomb potential, you have an electric field, but no magnetic field in the lab frame. So imagine that the nucleus of the atom is at rest in the lab frame, and you have electron orbiting the nucleus. Then if you put here B is 0, then you use this equation here for the electric field and the acceleration. This is Newton's second law. If you consider the non-relativistic limit, which is the relevant limit for atomic physics, you get this equation for the spin. Here you see a precession. You see that in the numerator here, the G factor is decreased by 1 unit due to this kinematic term. This is what you learn in quantum mechanics when you study the spin-orbit interaction. So this precession term here in quantum mechanics can be explained by using this Hamiltonian term. However, there is an additional term which is not accounted for in the usual treatment of the atom, for which we do not know yet what is the Hamiltonian. So we lack a fully consistent treatment of the spin. Why? Because if you consider this spin-orbit term, this adds a potential to the electron. So the acceleration of the electron will depend also on this term. It's a small correction. So as far as you want only to explain the spectrum of the atom in perturbation theory, this term is fine. But if you want to make a consistent theory, there is something missing yet. And this is still an open question. And now let us go to the second application, which is the one relevant for the Fermilab experiment. We consider a cyclotron motion. So we have a particle, a charged particle, in a uniform magnetic field. There is no electric field in the lab, so E is 0. And you know that this particle is making a circular motion. In this case, these here are the equations for the spin. You see that there is a pure precession term, and there is another term which depends on the difference, G over 2 minus 1. So if this term was 0, this spin would make a pure precession in the lab. It would follow the motion of the particle. It will make a fixed angle with the velocity of the particle. However, since this term here is small but not zero, you have a more complicated motion. Now you can solve these equations here, and you get these formulas which describe how the spin moves in the lab frame. You are seeing here that there is the unit vector in the direction of the velocity of the muon in this case, and the normal direction. Then there is the z direction, which is constant. So these two directions are changing in time with frequency omega. And then there is this rotating term with frequency a gamma omega. A is very small. A is the G factor anomaly. It is the difference of G over 2 minus 1. It is of order 10 minus 3. So this A gamma is a small factor. So here you have a slow motion, and here you have a fast motion. You can consider also the average value of the nonlinear term if you wish and sum it, but you should consider also that the nonlinear term is fluctuating in time. So these are the fluctuations in time of the nonlinear term, while the linear term is constant. Now, what they did in this Fermilab experiment was the following. They injected muons in the cyclotron, so with a uniform magnetic field, and they waited for the muons to decay. When muons decay, they decay in an electron and 2 neutrinos, or a positron and 2 neutrinos. In the experiment, they were positive muons, so they decayed in positrons. Well, neutrinos are very difficult to detect, so what they did, they detected the positron emitted in the decay. And they used this formula here, which expresses the anisotropy in the muon decay. The decay of the muon depends on the spin. So what happens if the muon is pointing, the spin of the muon is pointing in a direction, the positron emitted in that direction will be emitted at a certain rate. The positron emitted in the opposite direction will be emitted at another rate, and at an angle at still another rate, and so on. So the rate of emission of positrons depends on the spin, and the spin is changing over time. And this movement of the spin depends on this parameter small a, the anomaly. So if you fit the data with this parameter, you get a measurement of the anomaly. That's what they did. But they use a formula which is not correct. It is correct only on average. So I will write the formula for the anisotropic decay of muons in manifestly relativistically invariant form. So the number of positrons emitted by the muon goes exponential in time, of course, with the initial number of muons. And then you have the anisotropy here. Here you see the velocity of the electron times the spin of the muon. This is the relativistic invariant formula for the anisotropic decay of muons. Now, you can write this formula, for instance, in the rest frame of the muon or in the lab frame. In the rest frame of the muon, what happens? The spin is a purely spatial vector. You see, zero component here, time, and then spatial vector, S prime. And the positron will be emitted with a certain velocity, so its form velocity is given by this vector here. In the lab frame, however, the positron will have another velocity, and the spin in the lab frame has this form here. So when you write this scalar product, this invariant product in the lab frame, you will get this formula here. You see, there is the velocity of the electron in the lab frame minus the velocity of the muon in the lab frame times the spin in the lab frame. Now we have all these quantities here because I wrote before the equation for the spin here. So I know how it varies in time. The velocity of the mu, I know how it varies in time. It is making a uniform circular motion, so it's simple. I put these values here, and I get this formula here in blue, which is rather different from the simple formula that was used to analyze the experimental data. Now, if you make a plot of my formula in blue, you will find this curve here. You see that there is a fast movement, which is with the cyclotron period. There is a slow movement, a small oscillation, which is with this precession period, which depends on the parameter A. And there is an even slower decay, which depends on the lifetime of the muon in the lab frame, which is 66 microseconds, because they had a gamma of almost 30. The lifetime of the muon is 2.2 microseconds, more or less. So in the lab frame, it is 66 microseconds. Now you compare with the experimental data. You see this black curve is the raw experimental data. You see that there is a qualitative agreement with my formula. And here I didn't fit anything. I simplified things a little bit because there is a coefficient which depends also on time. Here instead, you see they draw also a red curve. This red curve consists in randomizing over time this black curve here. Why they did this? Because their formulas does not predict this fast oscillation. It predicts just this curve here. So they had to make this operation on the data. Now, if you take the correct formula and you make a time average over the fast time scale of the cyclotron time, you get that a value which is very close to the incorrect formula that was used. However, very close is not exactly close. I plotted here the difference between the time average and the formula that was used, and still there is a difference, a small difference. You see it's 10 minus 3. But still, this is a very sensitive experiment. They want to measure with the precision of a part per million. So this discrepancy, this which was not accounted for in the analysis of the data, could explain in principle, I don't know yet because I don't have the data, why there was a discrepancy with the standard model value. And that's what I want to talk about today. So I will end here. I will show once again my conclusions, which you saw at the beginning. So I've shown you how to define correctly the spin in the lab frame. I've shown that the movement is complicated. It's not a simple precession, but you can find inside this complicated movement a precession which is partly linear and partly nonlinear, in the sense that it depends on the direction of the spin. And as a consequence, we have seen that the data of this recent experiment need to be revised. And finally, I want just to give you some perspective of where do we go from here. On one hand, we should devise an experiment which allows to discriminate which definition of spin is correct in the lab frame. I strongly believe it is T and not S, but it does not hurt to check it experimentally. And this could be done, for instance, with the neutrons, because neutrons have no electric charge. So when you accelerate a neutron, or a beam of neutrons, you will measure the magnetic field due only to the magnetic dipole moment. Another open question that I would like to answer in the next few months, at least, I hope, if not years, I hope it will be months, is to make a consistent description of spin-orbit interaction. That is, to write the Lagrangian for that, to find the Lagrangian for that spin equation in the minkowski space that I showed earlier. And there are a lot of questions. How do you include Stern-Gerlach force? Then you should decide what is the correct model of the magnetic moment of the electron. Is it Amperian or Gilbertian dipole? And then you should find the correct Hamiltonian in the non-relativistic limit. And the most pressing thing to do, I think, is to recheck the analysis of this Fermilab experiment and to verify if there is actually a deviation from the standard model or not. Because once you account for this this corrected formula for the muon decay, in principle, your error bar should increase. And that is all. So I thank you for the attention, and I am here to answer your questions and your doubts. Thank you.
Thank you very much. Thank you very much for the very nice seminar. Let me ask you some questions quickly, not scientific yet. I understand that these results have been published already, right?
No. So the bulk of it is submitted to PRA. I couldn't find a proper journal. I thought PRD would be the correct journal, but I couldn't find a section where it would fit. So for now, it is PRA. And then this comparison with the Fermilab experiment is something that I found last week, basically. Okay. So when I said I would give a seminar, I didn't know about this yet. So it's a fresh result. And yeah, I think this should I should contact the people at the Fermilab to see what they think about this.
Sure. Is that already in the archive?
It's on ResearchGate.
Okay. Because I gotta ask you in an email today or tomorrow to send the slides to me so that we can post together with the. So if you could add to these slides the preprint that is in ResearchGate, we post it together with the YouTube video. So if that's okay with you.
Yes, definitely.
And now the seminar is open to questions. Anyone has a question? I have one. Do you, if I understand, this is a general, would be a general correction to any kind of spin orbit term. So this should imply a modification also in the usual spin orbit terms that we have for solid state, like Rashba, Dresselhaus, or am I mistaken? From what you said, the correction applies to the spin orbit interaction in an atom, but yes. That's basically is the same mechanism for the spin orbit interaction that happens in solids like Rashba, Dresselhaus, and other kinds of spin orbit interactions. Do you think that, I understand that the effect is small, but it's there, right?
Yes, it's the effect would be higher order than V over C. So for what concerns the the precession it's very small. What bothers me is the other term, the symmetric term, which gives you the Lorentz contraction, which is small, but it seems it is of the same order of magnitude in principle. So let me see if I can. You are not seeing here. I need to go back to the slides.
The screen share has ended. We are
Yes,
not.
Okay.
Okay.
It now. It's not up. It's not coming up. But yeah, I do not understand yet, for instance, how this is the same as the precession term, but there might be some combination with the dynamics of the electrons, which makes the term smaller than the precession. So what I'm talking about is this here.
The red term.
Because if you take this red term, you will find a time-dependent rotation, which adds to this rotation here. It's the nonlinear term, which will depend on the direction of the spin. And you will find some other term which describes how the spin changes in length due to Lorentz contraction. Usually this term is negligible because for atomic physics, the velocity of the electron is 10 minus 4c.
Okay.
So, but you cannot neglect the precession term because it is small in principle, but it accumulates over time. So it ends up being detectable. So maybe this is the explanation. There is a small contribution that accumulates over time, and the other does not.
Okay. So any other questions? Luis, please.
Okay.
Hello.
See you, Antonino. Very, very nice. Thank you.
Thank you.
As you know, I'm by no means an expert in this area, but I understand there is a QCD calculation which does give agreement with the experiment. Are you aware of that?
No.
Very, very recently. Yeah.
No, I'm not.
It's a group. It's known by PMW, right? That's because the name of the towns was Bern and but they get agreement with the experiment, and it's based on a very large QD calculation, which hasn't been produced. So there's question whether it's accurate.
Oh, yeah. I'll have to check the reference then.
Yeah, I can send you a friend if you have any, I'd like to hear about them. Okay.
Thanks.
But this was very nice. Thank you.
Oh, thank you. I'm glad that you appreciate it.
Any other questions? Any more questions? It's quite involved. I think Edson has a comment.
You can finish your comment. All right. Thank you for your talk. Very nice, by the way. My brain is in a rotating frame, which I didn't distinguish. Maybe I need to bring it down to my office reference frame. But my question is maybe very naive. I'm not really I'm far away from this area, you know.
Me too, actually. It's the first time that I go into high energy physics. It was a coincidence. so
yeah, but you spend some time studying this, and you are a specialist as compared to my expertise. So you never mentioned, as far as I remember, you don't mention the Dirac equation. So are these everything consistent with Dirac equation? Sorry, maybe
yes.
very naive and really obvious.
So, because the Dirac equation gives you a G factor exactly 2. Starting from the Dirac equation alone, you cannot explain.
Yeah.
You have no.
So you need to include extra term then.
Yes, I know that this G factor anomaly is explained theoretically by including extra self-interaction term in the electroweak theory. I don't know exactly how it is done. I've never done it myself. But yes, your Dirac equation alone is not sufficient.
So, but this is a dynamic effect. Just correcting the G factor would not be enough, right?
I'm sorry, I didn't get the question.
But since your term is a dynamical term, so probably only correcting the G factor would be not enough.
Only correcting
the G factor in the G factor that
appears. No, here I am taking the G factor as given. So I'm not making a model explain the G factor. I'm taking it as given and then writing the equation for the particle having such and such G factor. I don't know if this answers your question. I'm not even sure that I understood completely because the audience.
I'm pretty sure I didn't understand, but I'm trying to. Okay, thank you.
Well, I think that these students probably are still scratching their heads, trying to follow the many transformations you did and all the. We don't, unfortunately, we don't have an advanced relativity course in our graduate program. Maybe it's time to include one. Do you would volunteer to teach relativity in the?
Yeah. Next semester, I'm going to teach a basic course of relativity.
You could think about in the next few years to expand it. You know that we are trying to hire an astrophysicist or astronomer. So the chances of keeping students here that would be interested in more different things, like different from material science, that is our strong suit, will increase. So maybe it would be nice to just think about. So it's your fault. You gave the seminar, so now you have to.
Show the consequences. I have to face the consequences.
You have to face the consequences.
Yes. I would like. So yeah, basically, after this course on relativity, the problem is that. Since it will be a remote course, you have only 18 weeks or so.
Okay.
Which is very little time to make an expansion. But maybe the other semester.
The other semester, yeah.
I hope there will be
enough students.
Face lectures. Then yes,
okay.
Definitely.
Okay. So if there are no other questions, we should thank the speaker again. Thank you very much. Very nice talk. And I hope that you managed to convince the people at Fermilab.
Well, I don't know who to contact yet. because there is a list of names, but there is no corresponding address. So I don't know, I don't know the corresponding author yet. I'm looking.
I assume that is a huge list of names, right?
Yes, yes. And two of them are deceased.
Are deceased?
Deceased, yes. It's strange when you see the list of names and the footnotes. But yes, statistically, when you have such much.
Yeah, the chance increases, right? Yeah. Okay, thank you very much. I'm gonna send you an email today or tomorrow asking for the